Okay, so just the course summary, just 5 minutes or 5-10, well, I guess I will finish in 5 minutes. So, it was a very broad course, okay, intentionally. I did want to uh, uh, give a broad picture, at least. I mean, it's a lot of things I learned myself. Okay, so that's so let me just tell you the what we did, a summary. Okay, so this interaction of fields. We hardly dealt with particles. Of course, there are people who do like Ising spin, they work with spins, but then they make a field. But we just worked with fields, phi 4 field, velocity field, temperature field. So, this was in this course, at least it was interaction of fields, classical or quantum, equilibrium or non-equilibrium. So, I suppose you got basic ideas about all this different aspects, though quantum we did not get too much into detail, and I hope some of the projects will give us some idea on um, to the class. Okay, when you will sit in the class. So, just to tell you that this is not, I mean, there everybody has done field theory. It is not that this is first time you heard of fields. So, electromagnetism is a field theory. Maxwell equation is all fields. Of course, you also worked with fields with particles, but waves, electromagnetic wave is field, and interactions of waves which can get nonlinear, which is not, I guess you have not done too much of that or no, probably nothing of that. So, that is a nonlinear field. So, that is a quantum optics, people work with interaction of fields, okay, or this electromagnetic wave coming through the atmosphere. So, they get scattered and there is a nonlinear effect. So, that is part is a higher order fields or quantum mechanics. You have a wave function and you discuss with fields, but typically that was linear, I believe. Okay, you did linear. So, gravity also. So, if you do non-relativity course, that is a field. But in this course, we covered these stuff. Okay. So, formalism of I did first start with formalism, Lagrangian, Hamiltonian, symmetries, conservation laws, and I hope you understood this part. So, we can write down Lagrangian of fields. Okay. Hamiltonian we can derive given the Lagrangian. Noether theorem is was a very important theorem. Then quantization. So, we can quantize these fields as soon as we bring in quantum mechanics, then these fields are quantized. Okay. So, the commutation relation comes, which is not there for classical fields. So, in classical fields phi k, phi p, I mean these are you can just multiply, no problem, but in quantum mechanics you cannot just multiply, these are operators. So, they become operators and time order products and commutation. So, there are commutation relations for these, right. So, quantum calculations have additional complication because of quantization condition. Perturbation approach, I hope you got a gist of how to do perturbative calculations, and I think basically from the middle of the course we have been doing huge number of examples of perturbation. So, phi 4 theory is a very important theory, and I did in detail Wilson theory of phase transition. So, we could compute those exponents which are very important exponents and which has won the Nobel Prize for Wilson for sure, and it led to lot of new discoveries. Okay. So, renormalization group, in fact after Wilson it got a new interpretation. Okay. So, I hope you got the gist of that, and then we did mass and charge renormalization of phi 4 theory, but that idea can be easily generalized, or it has already been generalized, but you can approach that problem of QED, mass renormalization. QCD is more complicated, but QCD also I gave you some idea that it's similar idea works for QCD as well. This is called asymptotic freedom, right. So, charges, so in QED if you separate the charge they become free, or if bring them closer the interaction increases. But what happens in QCD? When you bring them closer it becomes free. Okay. So, the quarks are, when they are close by they are free particles, but you separate them out, then they become the interaction increases funnily, right. So, quarks cannot be separated because it requires infinite energy to separate quarks. So, all that can be derived by this renormalization. We can compute the coupling constant, how it changes with Wave number. Then we started non-equilibrium field theory and fluctuation distribution theorem by example, and then we went to hydrodynamic turbulence, scalar turbulence I did today, KPZ, weak turbulence, and I hope you got the idea that what is the difference between equilibrium and non-equilibrium. Okay. So, equilibrium has no frequency, okay, no time dependence, but non-equilibrium has time dependence. Equilibrium has no energy flux, energy flux is 0 in equilibrium, but in non-equilibrium we have energy flux typically. It need not be constant, but we will have energy transfer across scales, and that leads to breaking of detailed balance. So, that is what I did mention in the class, well not mention, I think I did in quite a bit of detail. Okay. So, similarity in contrast. So, like for example, this frequency dependence I emphasized on many times. Also, KPZ RG was very similar to Wilson RG, except there was a frequency dependence here. Of course, that made the life more complicated, but if you know Wilson RG very well, then you can get the idea of KPZ RG. In fact, we can do all that stuff. Is very similar approach was adopted by the authors, and it is now textbook material, you can do that. So, the issues which are still part of unsolved problems, and there is their activities, anisotropy. As I said, if I apply temperature gradient, then the field theory becomes anisotropic, okay, or apply gravity, then doing field theory is complicated. Okay. Many fields like MHD has magnetic field or polymers, that makes a problem. Now, there is a new direction called exact renormalization group, exact RG. Okay. We did not do it, but this is another area. Non-perturbative tools, in fact, this is connected. Okay. I did not do in the class, and these are things which we did not even touch upon, quantum gravity and string theory. Okay. So, these are challenges if you are interested in field theory, and okay. So, I just wish you luck. So, apply to new areas, okay, and these are open fields. Unfortunately, not many people are working on this right now in analytical field theory. Okay. In turbulence, there are very few people who work on on field theory now. Essentially, they have gone into applications like soft matter applications or simulations. So, yeah, in some sense opportunity for people who are interested in analytical work, that you do not have much competition, but it is also true that it gets hard to publish these papers because it is not fashionable anymore, at least, well, yeah, I would say it is not as much in fashion as before.